So I just start sharing my screen. Good morning, everyone, and welcome to this first presentation of today of the Groundbreakers Tour. I have the pleasure to start today with my favorite topic of skiing. So my presentation today focuses on learning of a data mining project that I did last year with some colleagues of mine. So this will be an introduction into making predictions with Oracle data mining. If you have questions, please ask them in the Q&A panel. I try to answer them at the end of this presentation. We will probably have enough time for this. So first, something about me, just short. My name is Jasmin. I'm a database developer, and since June, I'm an Oracle ACE. I work mostly in data engineering and focus on automation of development processes. So my topics that I work with are mostly testing, continuous integration, and this around the database. And I also do program some PL SQL. So why do I talk about data mining today? You cannot find that in the list that you are seeing here because it's not one of my main activities. I'm currently finishing my master's degree in business information systems and computer science. And part of this is research that we do together with companies. I'll explain later a bit more about this. But since we are talking about skiing, you get a second picture of me. This is also me while skiing in the Alps. I have been working in the past as a skiing instructor and spent most of my winter weekends on skis. And that's why this project was also very exciting for me too. You can find me on Twitter, and I have a blog on Medium where I write blog posts. So now, what are we going to see during this presentation? What will I talk about? We have three things. I will start with an overview of the task that we had at hand. What was the goal of it and what should be achieved in our project? Then I continue with how we proceed. So how did we tackle this task? And finally, we will have a look at how we did the implementation of everything. Now, why is this presentation about data mining? As I said before, I'm currently doing my master's degree part-time in business information systems and computer science. And one part of this master's degree is doing research in university projects. And those projects are usually conducted together with industry partners that we have. And last year's topic was data mining and predictions. So all the students got a prediction and research task that they needed to solve. And our group of three was lucky to get a Swiss skiing area as an industry partner. Now, what task did our industry partner needed to solve? So something about skiing areas. So a large skiing area in Switzerland consists of many different components. They have ski lifts, they have restaurants, they have staff for operating the lifts, staff for the restaurants, staff for search and rescue, as well as administration and back office and all kinds of people there involved. And usually they are organized like a normal enterprise. But the difference to a normal enterprise is they have a large variation of their staffing because this depends on how many people are skiing in the area. And this depends on the day of the season, on the weather, on the snow, and on many other parameters. So this means that some of the staff must be operating on all days of the season, but others need less staff when there are less skiers in the area. So staffing varies with amount of tourists that they have. So the task at hand was to predict how many skiers are in the skiing area on any given day in the season. The reason they want to know this, they want to be able to plan the amount of staff that they need ahead. So if there aren't many skiers there, there don't need to be many waiters in the restaurant, for example. And if it's a sunny weekend, they expect to have more skiers on the mountain, and the restaurants need all the staff that they have available. So to have a proper amount of staff, this also means save a lot of costs for them. So if they have too much staff, and only few skiers, that means that they have higher expenses. And since they are profit-oriented, this matters a lot. And this is called time series forecasting. So the goal of time series forecasting is to make accurate predictions about the future. And this is exactly what we needed to do, some accurate predictions about the futures. Now let's have a short look what skiing is. I'm not sure if everyone is aware of what skiing is, so we have a look at that. So Wikipedia says skiing is the action of traveling over snow on skis, especially as a sport or a recreational activity. And in a skiing resort that our industry partner runs, skiing is especially downhills. And then this looks about like this. Now, but why do skier number vary? And why don't we have just the same number of skiers on every day throughout the season? This is mainly because we have different types of skiers that have different interests and different time schedules. There are mainly 4 types that we'll have a look at. We first have the local skier. He lives around that skiing area and goes skiing in every 3 minutes of his time. Then we have the weekend skier. He only goes skiing on the weekend. He works during the week and only when the weather is nice. He doesn't like having too much wind, fog, or cloudy skies, then he just stays at home. The third skier type is the holiday skier. It's mostly families that will stay in the skiing region for a week during the school holidays. They'll buy skiing passes for the whole week because it's the only time they have for skiing. So they ski every day for this week to get the most out of it. And the fourth one is the single day opportunist. He's very flexible in his schedule and goes skiing for single days when the weather is nice and stays home when it isn't. So those 4 types of skier lead to a number of skiers on the mountain that is depending a lot on 2 factors, the 3 factors, the weather, the holidays, and the weekend. So the task at hand was to predict how many skiers are in the skiing area on any given day, to plan the amount of staffing. So if there are not many skiers, there don't need to be as many waiters in the restaurant. And if it's a sunny weekend, we need more staff. So the amount of staff on a mountain correlates with amount of skiers. And having a proper amount of staff means also saving a lot of costs. Now, if you want to start a prediction, you need data, a lot of data. Let's have a look where we got that from. A first set of data was provided by the skiing area itself. So they provided some historical data for the last 10 years. So we knew how many skiers were skiing on every given day in the past. They also gave us information about their visitors, where they came from, the countries of origin, the duration of their stay, where they stayed, and some other information. From fcall.ch, we took information about holidays of the different visitor countries. On the portal of Meteo Swiss, we got data about the weather from the past 10 years, because that obviously matters, like wind speed, snow, rain, barometric pressure, humidity, all those weather information you can possibly think of. On the Swiss Open Data portal, we got historical data about the national economy over the last 10 years. When we had all this data, we realized it was a lot. So we just gathered a lot of data. We had many features in the data. It wasn't big in volume. We had only a couple of 100 megabytes, but in variety, it was very diverse. And only the weather data consisted of more than 100 features in the data set. And we will discuss those challenges a bit later when we come to the creation of our data set. Now, what tools did we use to make our analysis, or what did we decide to use? As a university project, we have given requirement that only 3 tools can be used for research. So we decided to use Oracle Autonomous Cloud for our data store and machine learning platform. We only used the tools of the Always Free database, and not Oracle Analytics Cloud, because Oracle Analytics Cloud is obviously not a free tool. The second thing was that we needed to decide how we are doing our data analysis. We needed to know if our data is skewed, how it is distributed. For this, we used Tableau. We probably could also have used an Excel spreadsheet for this, but it was mainly about plotting the graphs and looking at the data, how it's distributed, and if we need to take any action to clean it before. For all the data engineering part, we use SQL Developer, because SQL is, the best language to edit your data. Now we have decided upon the tools we are using, but what else is necessary if you want to start predicting stuff? Mainly you need 3 things for a successful prediction. First, you need to have a bunch of data that we just gathered. And this should be historical data of the factors that influence your prediction. In our case, it would be useless to have flight information because people rarely go skiing by plane. But it would be useful to have the dates of the local holidays, for example, because people tend to go skiing more often on weekends and on public holidays for obvious reasons. The second thing is know what you want to predict. Just having a bunch of data doesn't automatically provide you with wisdom. That's why it's important to have a well-formed question you want to answer with your data. It's a lot easier to work on a well-defined target and also know when this target is reached. It's also good to know when to stop optimizing your model. For this, you need certain criteria that you have to be met, like the prediction must be accurate in 80% of the cases. The third thing is you should have some basic statistical knowledge. Not a lot, but some basic understanding of statistics will be necessary to interpret your data and make statements about accuracy and precision of your predictions. The rest can you compensate with very good Googling skills, or you know the right people that can help you figure out things and tell you how to go forward, for example. Now, if you want to predict something, where do we start? What's our entry point? As I said before, we start with asking the right question that we really want to have an answer to. As I also said, it doesn't matter if you have all the data in the world if you just don't know what to predict. Because if you don't have a question, it would be a waste of time just to do all the engineering work when there's no real outcome of it. And based on the question, it might be that you have different data that you need. If I ask, for example, at which wind speed do we have to stop the lifts because it's too dangerous, I probably need weather data and engineering data of the lifts to make the predictions, but maybe also some sensor data of the lifts to see how they react in different wind speeds. If I ask, how many skiers are in the skiing area on any day in the next 10 days? I don't need any engineering data of the lifts, but probably some data from the past years, along with weather data and economic data. The third example questions how many skiers eat spaghetti in the skiing area on any given day in the season can then be probably answered with restaurant sales data and the data of sold tickets. But maybe there are other factors that influence spaghetti consumption on a mountain that we are not aware of. And And that's why predictions, to make predictions is always a bit of an experiment. You can experiment with the data that you have, but you can never be sure if you have missed vital data. That's why you should analyze the data that you have very well. Maybe there are factors that are completely irrelevant that you see as vital for the predictions that will falsify your results. Now, if I have a question that needs to be solved, how do I need to prepare my data set that it is ready to use in a data mining model? The goal must be to have one single table that contains all the necessary data to train or test the model. So we need one table where each row is one data point. The granularity must be consistent. Either you have the data points per hour, per day, per unit, per year. It must always be the same unit in all the data points. We decided, for example, to have the granularity of days, since our prediction question was how many skiers per day will be on a mountain. So the granularity was an easy decision for us. The data needs to be well labeled, that you know exactly what is in which column. It should be annotated and cleansed. So this means you have to resolve keys that are not self-explaining, and you have to aggregate numbers to the granularity needed if you don't have them in the granularity that you want to have in your data set. For example, if you have snowfall data per hour and want to have it per day, you need to aggregate the data from hour to a daily measurement. Now, if I have all the raw data now, the logical next step would be to arrange my data set as we said. Now let's have a look how the data set needs to be arranged exactly. When building a data set, you should aim for a diversity of data. You should gather both internal and external data when you are a company or a skiing region, for example. So the goal is to build your unique data set that will be hard for your competitors to copy. And that's why we took internal historic data of the skiing region, as well as weather data and economic data that was external and publicly available. So this mixture is then really unique. Data mining applications do require a large number of data points. But this doesn't mean that your data set needs a large number of features. The important thing is we want meaningful data related to the project that you have or the question that you want to answer. You may possess rich, detailed data on a topic that simply isn't very useful. And that's why you should reduce your data to the one that you really need. So to those features that you really need. And you also should make some assumptions about the data that you require and record those so you can test against them and assure that they fulfill your standards that you have to control your data if it's good enough or it isn't. We said before that reducing your data is very important. This process is called feature selection. Every row you want to have in your dataset table is called a features, as you can see here with the different colors. A random brainstorming of possible features often results in a large list of attributes. Not all of them are necessary to build effective classifiers. Selecting only a subset of those initial attributes can help decrease the complexity and also decrease the computing time of your algorithm. And some algorithms are just not good at dealing with irrelevant or redundant attributes and will deliver a lower quality of the model and of the predictions if you have just too many things in them. So the more noise you have in your data, the worse the algorithm will perform. For example, it is important that the attributes don't correlate well with each other. They should be independent. As an example of two features that correlated in our data set was wind speed and air pressure. The wind speed is determined by the rate of air pressure change between two pressure areas. So the greater the pressure difference, the faster the winds. So that's a big correlation. So those attributes would provide us more or less the same information if we took both into our data set and we had to choose only one of them. If we have decided which features are useful and which ones we want to use in our data set, we end up with a list of our final features, which is a subset of all the features that we had at the beginning. Now we have decided of the features that we consider useful in our data set. What are we going to do if values are missing or it's just not complete? Missing values are a very common problem in a real-world data. Either there is no data point or it is not complete. Both cases are a problem for many algorithms because they cannot deal with them or misinterpret them. So while building the dataset, one has to find a solution on what you want to do with those missing values. And we have these 5 possibilities on how to treat missing values. The first one is data objects with missing values can be eliminated. This will result in deleting the row in the table, for example. The second one is the attribute with missing values can be eliminated from all the data objects. And this will result in deleting the column and therefore deleting the whole feature. So we should have known that in the feature selection before. If it's not complete, we probably cannot use it very well. For missing data, it's also possible to insert a special value like not available and later ignore those values in the analysis. It's also possible to insert a summary value like the mean or median for missing values, or for categorical values inserting the mode. The fifth possibility is to copy the value from the data object that is most similar in terms of all other attributes and insert this value into the missing value. This is the most often used way of handling missing values. There is also a general consideration on building the dataset that you should keep in mind. Larger amounts of data often outperform more sophisticated modeling methods. That means if you have a very large amount of training data, you could choose an algorithm with a lower accuracy but greater speed of learning, instead of using only a sample of the data that a highly accurate algorithm can cope with. So the more data, the better. If you only have a small amount of data, the accuracy won't be very good, as seen in the picture here. If you have a lot of data, it improves with every data set that you have. So if you can, always train your model with a very large data set. This is also the reason why you should keep your data in the database while training a model. You have the performance and the security of the database and are unlikely to run into performance issues. If you export your data into some CSV file and then train your model on your local computer, you are probably unable to use the same amount of data and not with the same performance as well. And you also have the problem of the security of this data because it's on your local machine. And you can copy it, you can distribute it, and yeah, it's mostly not a good thing to export the data out of the database. So always keep your data inside the database and make your models there. It's where data belongs. Let's go shortly back to the basics of the data mining process. Data sources can have very different shapes. They can be other databases, you can get some flat files, there can be news feeds or IoT data that are read. And this data is collected and pre-processed and it is then stored, for example, in a data warehouse. Based on the collection of the data in the data warehouse, data sets can be put together. Important here is to say you should usually take the algorithm to the data and not take the data to the algorithm, as I said before, so the data stays in the database. It just makes your life a lot easier. So you create your data set and you create the data set based on the data of your data warehouse. And once you have your data set, you can train your data mining model. So the model can then be used to make predictions or make categorizations or build data clusters, whatever your use case is. And those predictions are additional information to our existing knowledge that we have. This can help us take the right actions when they are correctly interpreted. So additional information lead to action. So the goal of data mining is to extract information from a data set and transform the information so it can be used further. Data mining is divided in supervised and unsupervised learning, as you can see here. With supervised learning, the algorithm learns on a labeled data set and tries to find a specific solution to a question that you have. And it is done with classification or regression. So like in our example, we have a labeled data set of the skiing data where we know exactly what data is provided to our regression model. With unsupervised learning, the algorithm learns on an unlabeled data set and tries to find pattern in the data on his own. This is the case with clustering, for example, association analysis and anomaly detection. Now that we know what data mining is, let's have a look what's inside the data mining model. What do we need to predict something? Inside the model, you have an algorithm. And the algorithm is the thing that calculates your prediction. In the picture, you see a diagram of a linear regression with two variables, a dependent variable and an independent variable. In a prediction model that uses linear regression, the dependent variable is predicted with one or more independent variables. So the dependent variable is the thing that you predict. So through the shape of the data points, a line of regression is calculated that would then be the baseline for the next prediction that you want to make. But how are we going to find the right algorithm for us? So what's the right algorithm for our problem that we had? There are many different types of data mining functions, and each of them can have multiple possible algorithms to choose from. So which function is the right one for our question? Which can be used as a prediction model for skiing? We didn't select this very scientifically, and honestly, you don't have to, because every data mining function has a name and a short description in the Oracle documentation. And if you read this documentation and have a clear question that you want to solve, it should be very clear which data mining function you have to choose to go further with. So let's quickly go through all of our possibilities. Let's start with anomaly detection. Anomaly detection is listed as an unsupervised data mining function. It is described as a form of classification. It detects if a data point is considered normal or is not. So that's not what we need to get skiing days predicted. But what's about association? The documentation says that association identifies relationships within a data set. And that didn't sound promising to us. So that wasn't chosen as well. Let's have a look at clustering. Clustering defines groups in a data set, but we don't really want to group anything. So that wasn't the right one for us as well. The next one, feature extraction, is for creating an optimized data set. That could be used further in a model. So that would be practical to create a perfect data set, but not for the prediction itself. Then let's go to attribute importance. The attribute importance gives us the relative importance of an attribute in predicting an outcome. So that would be very practical also if we are doing measurements and are optimizing our model. So maybe later on, but not for predictions. And that leaves us with only two options left. We have classification and we have regression. Both of them can be used for predictions. Classifications are described as models that use historical data to predict a categorical target. And regressions are described as models that use historical data to predict a numerical target. So the only difference is that one predicts a categorical value, like the avalanche risk that can be low, medium, or high, and one predicts a numerical value that is a number. And that's why we decided to go with the regression, because we want the amount of skiers as a number and not as low, medium, or high. As I said, there are different algorithms for each technique to choose from. With regression, we have the following two possibilities to choose from. A generalized linear model multiple regression algorithm or a support vector machine algorithm. And here again, you don't necessarily need to study statistics to decide on the algorithm. You could just build two models with the two algorithms and have a look which one gives you the better results. The support vector machines divides the data point into clusters so that they are divided by a clear gap that is as wide as possible, as seen in the left picture here. Precondition to use a support vector machine algorithm is a dataset that has a known classification value to make the clustering possible. And the multiple linear regression is shown in the right picture here. It is used when we want to predict the value of a dependent variable based on the value of two or more given values. And that sounded very promising to us. And that's why we chose it. So the generalized linear model multiple regression was used for, in our project to predict the amount of skiers and out of the independent variables that we collected before. Now that we know which algorithm to use, how are we going to split the data into two sets? The thing is, you cannot test with the same data that you used for training the model. That's why you need to split them. You still want to use as much data as possible, but also need a certain amount of the data to test the model. For example, an 80% data set for the training and a 20% data set for the testing. Now, what's important when we split our data set? It's essential that your splitting is reproducible. So if you have to recreate the splitting sometimes in the future, you still want to get the same results as you got the first time you did that. And how is this possible in SQL? Let's have a look at some code. One way is doing this with Aura hash. Aura hash generates a hash value for a certain expression. This function is useful for generating random samples of data that are reproducible, like when we need a random 10% of the data, or a random 50%, or just splitting it in two sets. In the shown example, two sets that are equal in size would be created, so a 50-50 split of the data. And to create an 80-20% split of the data, one would set the maximum amount of buckets to 4, because the counting starts with 0, so then 5 buckets would be filled with values. The second argument you see here is the seed value. Aura hash allows to produce different result sets from the same data set with different seed values. With the 5 buckets that we have, we use 1 in the first query and 4 of them in the second query. And this results then in a 20/80 distribution of our data set. That was easy, right? Now let's create the prediction model. The overview of what we are going to build is shown here. We have our training data set that contains most of our data, let's say 80%. We need a settings table that tells our model on how to behave. If we have specific settings that deviate from the default, we have to define that. And out of those two, we create the prediction model. To test the prediction model, we have our test data table with the 20% of the data. This table has the same structure as the training data, but contains different data, and very important, does not contain the target value that has to be predicted. So with the prediction model and the test data set, we are going to make the prediction. It is then possible to compare the predictions to the actual data. That would be the target value that was removed from the test data set between the prediction and the actual data. And the results show us then how accurate our prediction is. Now, first we have to create this settings table. It looks like this. This is not really up for discussion since it's an Oracle standard. It defines the settings in your model that deviate from the default of an Oracle prediction model. So which algorithm you want to apply must go in there. And it looks like this. It has a setting name and a setting value. In our model, we inserted 3 things. The first one was the algorithm name. So we used the generalized linear model. The second one was we enabled automatic data preparation. It is enabled by default, but it's still very useful to show here because it transforms your data according to the requirements of the algorithm by itself. It doesn't change the data table, but it's transforming the data when the model is created. And the third one is the definition of how the missing values are treated. So if you still forgot to eliminate some values in our data set, we define here how the missing values are treated. And we chose here that we want to use the mean mode for it. Now, let's have a look how this goes in the database. We create the model settings table with setting name and setting value. And once this is created, we can insert the model settings, algorithm name, prep auto on, and missing value treatment. And if we then have the table over there, yeah. And if we then select from the table, should show anytime, yeah, we can select from the table and then get the values that we have inserted. And see here, it's the algorithm name, we have prep auto on, and missing values are treated with the mean mode. So to create the data mining model now, we have to use we used the DBMS data mining package. You have seen on the slides before where the settings were inserted. You have seen the package before mentioned. The create model clause requires us to define a name of our model. It is the object name that will be used further to reference our data mining model when we do predictions. It is the same as a table name, for example. The data mining functions defines the functions that we choose for the model. In our case, this is regression. Then we need to name the table that contains the training data. The case ID defines the column that labels the granularity. In our case, that was a date column, but it could also be a numerical column with a sequence number or something that just defines the granularity that you have. The target column name references the column in our dataset, in our training dataset, that contains the target value that should be predicted. Since the model needs to learn how to predict the skier number, it needs to know which value should be predicted and which values can be used to calculate these predictions with the linear regression. Finally, we reference the settings table that we created before, and then the model also knows which settings and which algorithm to use. But how do I know which models I already have in my database? Is there a possibility to know? Yes, there is. There is this all mining models functionality that tells us which models are already existing in the database. Great. We have a data mining model now, and now we want to use it. How are we going to make predictions? You see here, predictions can be done with normal SQL clauses. The prediction functions allows us to reference a model when doing a selection against the data set that lacks the final target value that should be predicted. We then get an output like this, a table with the days and the predictions of how many skiers will ski on a certain day. All the numbers that you are going to see are fake numbers here. Unfortunately, I'm not allowed to share the real data with you. But what we can see in the example result set is that on Mondays, we have a pretty low amount of people predicted, and on the weekends, the number increase. So to create the model, this looks like that. We create the model with the DBMS data mining function, give the model a name. It's the skier model weekdays here. The mining function is defined. The setting tables is defined, date ID is there, and then can select from all the mining models that we have. If you create a data mining model, it will automatically create you other objects in the database that contain information about this model. And as you see here, that those two are the models that already exist now in the database. And if we are doing a prediction with the prediction functions, we get the data ID that we select and a prediction to every row in this table. So for every day of the season, we get a prediction. But how do we know if this prediction is accurate? The number looks great, but are they really as great as they look? So the accuracy of a model refers to the percentage of a prediction that are correct, or in our case, how close to the real value is our prediction. But how can we measure this? The accuracy test should always be done with the test data and not with the training data to allow a fair assessment. So to evaluate the accuracy, we take our test data set, we remove the target value from the data set and let our model predict the amount of skiers. If we keep drawing a curve like the one in the picture while collecting training data, over time the model should get more and more accurate if we have done everything correctly. So this is also important to regularly test your model again while collecting data and to improve the model over time. It's not a one-time task that you can do, but more a continuous one that you have to do over and over again. Now let's test our models. What do the numbers say? In the table that you can see are our predicted values. And when you compare them to the real amount of skier, we see that they aren't that accurate. The column delta percentage tells us the accuracy in percentage between the predictions and the real amount of skiers. Although some of the numbers are not bad, like we have a 7% and a 13% variation, there are also cases when you have a 100% deviation between the prediction and the real amount. So that's not very accurate. So we need to improve these predictions, but how? We ended up with two possibilities that we could use to improve our predictions. The first one was feature engineering. That would mean we would go over all the features that we have and restructure and redesign them, choose other data points, choose other attributes that we have in them, and just come up with a new data set. The second option was to create multiple models, either one model per weekday or a weekday model and a weekend model to eliminate the variety that we had between the single days of the week. So we decided to go with option number 2 with the multiple models, one per weekday and one for the weekends to predict the models. With one model, we had this setup, and now with two models, the setup just increases, it doubles. We have two prediction models because we have two training data sets. We have two test data sets and get a prediction for weekdays and one for weekends that we can combine with a select statement again to get the predictions over the whole week. And with the two models, we never had a deviation in a delta percentage that was larger than 30%, as you can see here. There are no more red numbers, what means all the percentages are under the 30% mark. The differences in the predictions really improved with the two models. When we compare the two predictions, we see that the numbers improved dramatically from the first approach to the second ones. Now, of course, you can calculate those numbers yourself, but is there another way to do this? I said when you create a model in your database, there are other objects that are created as well in the schemas. And one of those are views that give you statistical details per attributes. The DM$VD view provides you with statistic per attribute, and the DM$VG view provides you global statistics about your model. This looks around like this. So if you select from the first view, from the detailed view, you get a list of all the values that you have and get coefficient, standard error, test statistics, p-value, lower coefficient limit, all these statistical values that you should have else have calculated yourself. If you do the global statistics, you also get error sum squares, dependent mean, all those statistical values about your model that you can interpret then. So our conclusion as newbies in the data mining environment was that overall it is very easy to learn, but it gets tricky when you have to improve your model. And if you have no deeper understanding of the algorithms and essential statistics, it will be difficult. So it's also essential to understand the domain that you are working in, because if you have to improve your data set, you need to know what other data is important. Data preparation is the most part of the work. You always have to improve your data set and re-prepare it to do models. Now, if you want to ask if I hand out the slides, yes, I probably will, but they contain a lot of pictures, so they're not very helpful. I have written a blog post that you can find on my Medium page. It's a lot shorter and gives you all the necessary details if you want to start making predictions. Yeah, now, what questions do you have, or do we have any questions? I quickly look.
No, we don't have any questions.
We don't have any questions yet.